Last time we introduced Newton's method, and I gave you some homework. Let's see how everyone is doing. Okay, find the difference. Okay, good. Okay. Okay. Oh, yeah. Okay. Okay, good. I hope you now understand how to use finite difference to evaluate the gradient. Actually, I only asked you to do first order derivative and second order derivative for one-dimensional problem. And at the end of last time, I show you how you can do use Newton's method for multi-dimensional problems. Now, let me show you how you can do that in MATLAB. So it's a programming time again. Let me turn off some stuff. Okay. Turn off. Okay. So I hope you still remember what to do for the one-dimensional Newton's method. And in my coding, I will be showing you how to do it for multi-dimensional problems, and also how we can utilize finite difference to evaluate the derivatives. I am going to start from scratch again. So I always like to clear the memory, clear the monitor, the command window, and close all. Well, close all the windows, all the figures you create. So if I rerun the program, everything will be reset. Now, if I want to do finite difference, I need to define a way to substitute into the function. I think I will again use symbolics. It's a much easier way to code for coding. This time I will use x1 and x2, so I'm solving a two-dimensional problem, so you can see it in a 2D configuration, a 2D figure. And let's say my function is x1 squared plus 10 times x2 squared minus 5x1, for example, something like this, or plus 6 times x2. Sum some second order polynomial with two variables. And because my x1 and x2 are symbolic variables, my f will be symbolic. I can use subs for plugging in numbers into the function. I will need an initial guess, so I will have an iteration number. I will start with 1. K is my iteration number, and I will use capital X as my variables. Now I need to make a decision. Do I choose the variable to be a vertical vector or horizontal vector? I think I will make them vertical ones. Because when we solve the problem, usually all the vectors are vertical vectors. So if I want them to be vertical ones, and for every iteration, I want them to be multiple columns. The initial guess is the first column. The next solution will be saved as a second column. So I can just only use one variable. In that case, I will say this is a column, comma, and K. That would be my initial guess. So column means whatever you use for the vertical direction, and horizontally kth column. Now k equals 1, so this is like a first column of my x. So initial guess 5, 5 maybe 5 and 5. So in MATLAB, if you use a semicolon right here, that's like a change the line. So it's a 5 and 5. So that's my initial guess. And then I will need to have a value called error to like an initial large number. So my while loop continues. So while error is larger than the small number you're going to use for termination criteria for convergence check. When this value error is large, you continue to do this while loop. Okay? So inside the while loop, first round, you will be evaluating many things. You need to, this is for multidimensional Newton's method. So you need to evaluate, let me say dfx and dfy. They are going to be the partial derivative of x with respect to x and with y. And later on, I will be needing to do ddf, or I say just dfxx, dfxy, and dfyy. So they are the second order derivatives. I'm going to name them like this. Once I compute those with finite difference, my gradient would be dfx semicolon dfy. And my Hessian is going to be dfxx, dfxy, dfxy, because dfyx is going to be the same as dfxy, and dfyy. That will be my Hessian, right? If you remember what we did last time. Do you still remember? Okay, now we just need to compute those. Then I have my gradient and Hessian. And Newton's method tells us the next round of x, k plus 1, equals to the current x minus Hessian inverse dot product gradient. That's the Newton's method. And because Hessian is a square matrix and gradient is a vertical vector, dot product, a matrix dot product, a vertical matrix vector equals to the multiplication of both matrices. So you can just use multiply right here. That's equals to the dot product that we're going to use. So everything that we need right here is just a finite difference. So in order to do that, I'm gonna define a delta. I'm gonna call it del, a very small number, for example, 0.01. I'm gonna use it for finite difference. Right here, you just need to have, basically you are going to do a substituting into f. And this is an interesting part. For MATLAB, you have to do it like this: x1, x2. Oh, you need to make it vertical. When you have this, I don't remember the English name of it, of this kind of bracket. Parenthesis, or I don't remember the English name of it. It's the definition for a set, and we use string to represent which symbol would be the variable. And since there are multiple variables, so when you put multiple strings together, you have to put it inside a set. And this kind of bracket is the definition for a set. So first input is the function, second input represent what are the variables, third input will be the values. So this is my value, right? My current x. However, I want to have small increment on x1. So plus delta times basically 1 and 0. So I only increase a little bit in the first variable. So that would be my first substitution. This guy minus the same thing without the increment. So no delta, right? So this substitute minus the other substitute divided by delta itself. Okay? So this is substituting into f with increment of, this is like a delta x, and then minus itself. Okay, we're going to use this value multiple times. So I think I will do the substitution outside and then plug in into the derivatives later on. Otherwise, I will be substituting f multiple times. So I should do, so I need to name those. So f with dx, f with dy, and I'm gonna call this f plugging the current x. And I also need f negative dx, f negative dy, and also f dx and dy. I need those. So this substitution is f dx, increment of delta x applied to x1. And this one is my current x. Just substituting the current variable. So once I rename those, I can just use them inside the derivative. Okay, so now it's easier to read. So over here, I also need increment on y. In that case, my delta will be applied onto a vector of 0 and 1. So here are the difference. This is increasing delta x1, and this is like increasing delta x2. Okay. So over here, my finite difference on y would be changing this guy to y. Okay? Actually x1 and x2, but in this case I use y. Okay, now I need to do finite difference a backward one. I need to evaluate the function value with a decrement. So in that case, you just minus delta x. And over here, negative, so backward. So over here, a minus. Okay? Last one. Last one is having a delta x on x1 and also having a delta on x2. So basically, 1 and 1. You apply increment on x1 and x2 at the same time. So that's everything you need. Now, over here, how do you do this? You basically apply the equation. First, having an x increment minus 2 times the current value plus a decrement. Decrement is negative dx divided by delta squared. Okay? And for the y, same thing, but over here change to y. This guy changed to y. For the basically partial derivative of f with respect to dx and dy, second order partial derivative. For this one, first one you are going to use this guy. This one minus the one in the front, this one. And then minus this one. And plus the original one. Divided by square of delta. Okay. So if you remember everything I taught last time, this is basically how you can program this. Just to remind you, let me turn on the iPad to remind you where those are. Okay. So what I did was, oh, I did it on the board. I never have it in my iPad. I did it on the board. So, well, then you need to check. You have to check the notes from last time. Okay. So sorry, I don't have it. Maybe I have it from the past time. This one. Let me see if I have it. This is the old one. But when did I introduce finite difference? I didn't. I didn't have. Oh yeah, here, like this. So, oh, I need to show you the full screen. So this should be pretty clear. This is for the gradient. So what I did was, when you have increment of delta x, if you are doing partial derivative with respect to x1, you apply increment on x1 only. Okay? And if you are having partial derivative with respect to y, you have increment on y. So in my coding, I substituted into f with my current value plus some increment. And depends on whether I'm doing this guy or this guy. For the first one, I increase the x1. For the second one, I increase the y. Okay, that was the part. And I made a mistake right here. This is a square. So for second order partial derivative, you have increment of x minus the current one plus the move backward. I think that was the proof for your homework one, right? Yes. In your homework, you are supposed to handing today. You just proved how you can use finite difference to solve for second order partial derivative. That was it. That was this. Okay? And the only thing that could be confusing or you may forget about it would be, let me remind you by writing them down. This one you may forget. So if you are trying to do partial derivative, second order partial derivative with respect to x and y, then this is how you do it for finite difference. And it's a forward scheme. So in the design, in a coordinate, if you try to memorize by a figure like this, it's easier. So basically, this one is this one. This one is this one, right? And this one is this one. This one is this one. So basically, you evaluate the function value at different locations. So this is where you are, your current x. You just want to check the slope of the two-dimensional function. You need to move forward to certain places. And this is like a way to evaluate a 2D space. So you need to not only step forward along the x direction, you also need to step forward along the y direction. And you can figure out, go back and figure out how come this is, if you having this minus these two guys and plus these divided by delta square equals to this, you can prove it by yourself, just like your first homework. But I always have this picture in my mind, so when I do coding, I know what to do. I don't really need to write it down and then remind myself what to do. Okay? So this is just for you to understand better about what I did in MATLAB. Is that okay? Yeah.
Is it possible if we have different delta x and delta y?
Yes, you can.
So
But
this means there's not delta square, so delta x times delta y.
then what you put at the bottom will be two different deltas.
So delta x times delta y.
But Why?
No, I just want to know.
Usually we apply same delta everywhere. So programming-wise, it's easier.
Yeah.
You don't need to define multiple deltas. And of course, if the curvature along x and y are so different, which means the slope along x and the slope along y are super different, then the accuracy of your approximation will be different if you choose the same delta. But in reality, whenever you solve with some random problem, you never know how the function looks like. So the easiest way to control your program is to use the same. That's how I view this situation. So let's get back to MATLAB. Okay. So if my coding is correct, this is already working. And once I have my new variable at the bottom, I need to have a convergence check. So the way I check was to compute the two norm. So basically the distance of a vector, the length of an error vector. So error will be, of course, you can use square root of x squared plus y squared, but it's not convenient. In MATLAB, you can directly say norm. Norm means computing the length of a vector. So just use norm. So the current variable minus the last one. Okay? So that would be how you can compute the so-called the two norm. Okay? Once you have the error, remember you need to advance k by 1. Last time we forget to do that. So supposedly this one can converge well. So let me call this Newton multi-dimensional. Let me try this. Typo. F dy. So F dy. Okay, try again. Okay, finished. K equals to 3. But you see nothing, right? So next I should be making some plots for you to understand what happened. So initially, let me have define a plotting zone. I'm gonna plot from negative 10 to 10. And I'm gonna say object function easy contour. Easy contour. F and so on. Hold on. And then I'm gonna easy plot the current variable. The first one and second one with a dot. With a dot. Black color. Marker size. 20. No, marker size too large. 10. And easy. Not easy plot. Plot. Just plot. Yes, just plot. Okay. And then display. Say initial gas equals to number to string the current variable right here. And it was a vertical one, so I'm gonna transpose it And then, yeah, oh, break it. Okay. What? Okay. So, plotting a contour to show the objective function, plotting a dot to show you where exactly the initial gas is, display a text about your initial gas. During the process, once you find the new solution, do some plotting again. I will be plotting the new variable, so k plus 1 right here. And I'm gonna draw a straight line to show you the moving trajectory. So plot again, but this time I need several more things. I'm drawing a straight line, so from the new point to the old point. Drawing a straight line. X2 comma k. Straight line, so straight. Use red color. Line width 2. Okay, and then I'm gonna display what you have after you compute the error. So this time x equals to this. So over here I'm gonna say iteration number equals to number to string k, and then comma space x equals comma space x equals to this, and then I'm gonna say error equals to some number to string the current error. That should be it. Okay. I did something wrong. The x transpose should be inside, not outside. Transpose is inside, not outside. We're gonna do it again. Okay. So it was too quick, but let's check what happened. From 5.5, the first iteration, it went to this value. Error was 5 point something. The next iteration, same solution, so 0 error. And what happened was, for the figure, I'm gonna say axis equal. Axis equal means now when the drawing was plot, when the figure was plot, it's not at the same aspect ratio. If I'm plotting the same width for x1 and x2, supposedly the space should be a square, but now it doesn't look like a square. If you say axis equal, the scale will be having the same length, so aspect ratio will be correct. So, and this time I'm gonna pause and then show you what happened. So I'm gonna pause before we. I think I'm gonna pause right here. Pause before we plot. Okay, let's pause right. So we run. Okay, so initially there's a starting point right there, and that's the initial gas. So after one iteration, it moved to the center. This is the contour of the objective function. Okay, and then one more time, it went to the exact same position. So since this is a second order polynomial, Newton's method was able to find the solution so effectively, you cannot, because the second order Taylor expansion was made so precisely, because the function was second order polynomial. So there's no error for Newton's method. That's why it goes to the exact solution immediately. Now let's try to solve a different problem. Let's try to just say multiply sine x1 plus x2. Just introduce some nonlinearity to the function. It becomes a different story. Okay. So now you can see the contour is very wavy, and it won't converge to the solution immediately. It may maybe jumping around. So let's check. Okay, first iteration, it went to somewhere else. Okay. We were lucky. Okay. Jumping around. Why is that? Because for sine function it goes up and down. Sometimes you bump into a new place and the gradient leads the movement to somewhere else. So Newton's method is not good for this kind of wavy function. Did I mention convex and concave last time? I think I did. I mentioned about the local minimum and global, right? If we have a function that has multiple lower points, we don't like it. We don't like that kind of problem. We call that kind of function concave. Let me go to iPad. There are two words you need to know: convex and concave. So because we are trying to find minimization, we are minimizing f. So a proper function, a well-defined problem is a problem that has a minimum point. So it's in a nice shape. We call this a convex function. The shape is, for Taiwanese, if I tell you the Chinese, you will understand more easily. I forget which one is which one. Convex. I think convex is this word. So only Taiwanese know what's going on. It's a Chinese character. And the other one, concave, is two. Okay. Only Taiwanese know. Okay. So if you have a function like this, then you have minimum going to the infinity, right? And you may have minimum on the left-hand side, you may have minimum on the right-hand side. So there's no exact solution. And a gradient approach will lead you to negative infinity without stopping. It doesn't stop. So it's not good. We cannot solve a concave problem. Okay, I'm not sure which one is which. So what is convex and concave? Okay. So if this puff up, then it's concave. If this go hollow inside, has a hole, then it's convex. So for minimization, you need a function that has a hole, has a bottom. Okay. Anyway, so for sine function, it's like this, right? So we don't like a function like this because it has some area like here, it's concave. Gradient approach cannot handle this kind of situation because it may lead the solution procedure to go this way, or it may lead the solution procedure to go that way. What happened was we had an initial gas, and then the gradient over this area may lead us somewhere. Maybe it leads us to a different place. And the gradient right here leads us to a different place. So we were jumping around. And it didn't behave very well. If we try let me show you. If we try a problem that definitely has a bottom, but has some nonlinearity, then maybe we can see a better approach. So let me try to make it a fourth order problem. If this is a fourth order, yeah, that should be it. Let's try to solve this. Oh, okay, I need to do that. Okay, now the function is fourth order. So the second order approximation is not accurate enough. That's why it won't go to the minimum directly. However, eventually it will. Let's zoom in to see what's going on. So it went too much and then went backward. I think the minimum is somewhere right there. So if we zoom in again, so it went all the way to the bottom and then went up again and stopped right here, somewhere around here. Okay. Now, do you want to see how we can solve a three-dimensional problem? Okay, someone nodded his head. So let's try it. But in order to do that, we need to figure out how to do plotting inside Meta. So anyway, let's save this one. And then save this. So it was a 2D code. So now I'm doing a 3D one. I'm going to open the let me change the name to 3D. So let me open the 3D one. Now, let me introduce a third variable. So in order to, and let me change it back to second order for easier solution process. So plus 6 times x to the third, maybe plus 9 x3, x3 here. Yes, that's a square. Initial gas, I'm gonna introduce one more, 555. The plotting zone, I need one more region. And then we can no longer use the easy contour. I will replace that later on. Initial gas, this line is okay. Those two lines needs to be replaced later on. So for plot substitution, here I will need f dz. So substituting into these. Over here, I need to change everything to the third order. So I'm introducing the third variable for every part. And over here for my delta, I'm introducing third dimension as well. And for the third one, this one, dz, you are doing increment on z here. Okay? Now, for the negative one, I need negative dz as well. So n dz, here is minus. Okay. Now for the dx dy term, I also need dx dz term, and I need dy dz term. So in this case, increment on x and y, increment on x and z, increment on y and z. Okay? I think that's everything I need. Then I need dfz. Here, change it to z. I will need a lot more terms right here. I need dfzz. I need df x and z, df y and z. I need those. So for the zz one, just change this guy to. Oh, last time we made a mistake. For the 2D code, there's a bug. Here. No. That was right. Okay, so here, here change it to z. Yes. Correct. Okay, now for the off diagonal terms, x and y. So now x and z. So change all the y to z. Now y and z, so xy to yz. Xy to y and z. The same thing here. Gradient increasing one more dimension, dfz. Hessian, here you should have df x and z. Second row, dfy x, dfxy, dfyy, and then dfyz. Third row would be df zx, basically zxz. df 3 and 2, so 2 and 3, yz. Then dfzz. Let me check. 1 1 1 2 1 3 1 2 2 2 2 3, yes. 1 3 2 3 3 3, yes. Correct. Now Hessian exactly the same. Plotting. Okay, I haven't gone to the plotting yet, so let me skip plotting for now. Norm the same, but over here for display. Okay, this, if I'm right, this should work, but no plotting. Okay. Yes, if I'm right, this supposedly is right. So I just need to figure out how to do plotting. In order to plot, I have a code. It's called the easy isosurface. Yes, it's a code that I create in the past. Because MATLAB doesn't provide you to plot isosurface multiple times. So I create this for this purpose. I need to save this file to the desktop. Okay. Oh, on my desktop, I already have it. Okay, so let me just open the one on the desktop. Open. easy isosurface. Okay. Two versions. This one. Okay. So if I use this, if my coding was right, the function now is f, domain is zone, and I remember is how many isosurface you want to plot. Let's say 5. I'm not sure if I need to do the f extreme, maybe empty. I think I don't need those. Am I right? F extreme. I think so. Maybe I don't even need to do those. Just double check. Oh, okay. Something is not doing very well. Let me check. And it's right, domain. Okay. Maybe the function doesn't look nice. Why? We'll try this. Why so non-linear? Okay. Maybe I change the change to a different. Okay. I kind of know what's going on. Change this. Okay. So there's a 3-dimensional contour. Okay, too many. Just plot maybe 10 of them. Okay. So from using this, you can tell here the minimum is somewhere here. Okay? And the warmer the color, higher the value. Colder the color, smaller the value. So from here you can see the minimum somewhere right here. Now what we need to do is to plot the points, but now you're 3-dimensional, so plot 3. Third one, marker size I think larger. Black color is okay. Over here, plot 3. This plot 3. Third dimension, 20. Here I need a third dimension, so no, like over here. Change to the third one. Did I have the pause? Did I still have the pause? Yes. Okay. So let's run it. So initially, our point is somewhere at the middle. After one iteration, it moves. Now we can see it. Okay. And did you see our movement is kind of perpendicular to the contour? We're supposed to do that because I should say in the next method we should be moving toward the perpendicular direction, but Newton's method is smarter. it will move along along some direction that has been rotated a little bit. And how much it was how much rotation was made? It was based on the inverse Hessian. So what do I mean by that? If you go back to see the equation for Newton's method. I don't have the 2D notes right here. So let me use the old one. Okay, on Newton's method. That was the proof. And I want to get my equation. That was the proof. Last time I spent a lot of time proving. I don't think that's necessary. Okay, over here, you have a, let me make it full screen. You have your current point. Your new point is supposed to be located at somewhere from your current point with additional movement. So we want to move along the negative gradient direction. Think about gradient. It's how much function value increment per movement along x. So if you increase your x, your function value increased by a certain amount. So usually, if you move along gradient f, that means you want to move toward the direction with function increasing. Because if you increase x a little bit, your function value increases a little bit. But if you move along negative gradient, that means you're moving toward the opposite direction of the gradient. So in that case, when you increase your x, your value decreases by delta f. That's why we are always trying to move along negative gradient. However, Newton's method will have a pre-multiplier right here, kind of change our moving vector. And Newton's method, the inverse Hessian, will be changing that direction and also changing how much you move. And the magic came from how it was derived. Later on, there are some other methods. They don't want to use Hessian anymore. Because to do Hessian, you need to do a lot of second order partial derivatives. You also need to do inverse. It's so troublesome. And it's computational costly if you truly try to implement it, even in a computer. So people try to replace this by some other way. But the new method doesn't have the magic of negative Hessian. So the next method I'm going to introduce will be moving along negative gradient, but without knowing how much we should move. So we will be moving toward the perpendicular direction against the contour, but we need to figure out how far away we move for each iteration. So later on you will see we will be trying to figuring out what's the value, what's the pre-multiplier right here. And then iteratively, we always check what is the current gradient. We will be changing our moving direction later on. So let's check on the method code again. From the code, you can kind of feel, okay, it seems like it's very close to the perpendicular direction against the contour, but it's not exactly perpendicular. Next iteration converge. Let me try to change the function value, then you'll realize it's actually not moving toward the real perpendicular direction. If I change this to a greater value, let me make x2 and x1 having a different curvature, we can say that. Then you can see how obvious. No, I should change x3. Let's try 10. Okay. So if we are moving toward the perpendicular direction, the moving vector may reach this area, right? But Newton's method will not just move along the perpendicular direction. It will just go straight to the minimum point. Okay. So it's really cool to see through the procedure, right? Let's try to introduce a little nonlinearity to this. This time, maybe multiply, I don't know. Multiply or power to the 1.3, something like this. Not sure what's gonna happen. Okay, so the shape changed a little bit, but it's not quadratic anymore. So it will take multiple iterations to converge. Really? Okay. Newton's method was too powerful. It converged still very fast. We don't see it. Let me try. Oh, by the way, marker size. I don't know why the marker size is so small. Marker size 20. Anyway, how come this guy is so small?
Maybe because it's outside the box.
Say again?
Outside the box, the point is moved out because the rays only minus 2 until 10. So maybe it moved to other side of the box.
Really?
Maybe, I don't know. Maybe it look like that, I guess.
Oh, it's somewhere else. Okay,
Yeah.
okay. That's true. The solution is somewhere else, maybe. Let me try a different problem. You may be right. It doesn't draw. It draw nothing. Okay. Let's try sine, cosine again. I have no idea how it looks like. Okay. I have no idea. Let's see. Okay, the solution is everywhere. Also, I should be plotting this whole thing in a wider range. Much wider range. Okay, let's see. If you view this whole thing further, you don't see the sign too much. But anyway, let's see. Such a little movement. Okay, it's over here. So it's actually okay to view closer. Maybe this. Okay. final observation of Newton's method. Okay. Okay. So you do see Newton's method try to make a turn. Okay. Okay. Anyway, that's Newton's method. Now I want to move on to what I'm going to introduce today, which is so-called the steepest descent. And in steepest descent, I will be showing you why people try to use so-called steepest gradient direction. So we need to recall, this is the old code. Oh no. So in today's lecture, we're going to review multi-dimensional Newton's method. So it looks like k plus 1 equals to k minus Hessian matrix, substituting in the kth one, the inverse of it, dot product, gradient, the kth variable. So that was Newton's method. And the inverse Hessian was doing the magic. It helped the iteration process to change the moving direction from negative gradient toward some new direction with a proper moving distance. So negative inverse of Hessian is very powerful, but very costly. So one easier approach could be something like this. Just replace it by some scalar, some number. We call this one so-called step size. It's just a pre-multiplier, just a number, and it will define how far away you move away from the current point. The negative gradient defines the direction. And alpha defines how far away you move. If alpha equals to 0, you have no movement. And we are supposed to move along the negative gradient direction. So alpha is supposed to be positive. Otherwise, we are moving backward. We are not improving. Okay? So supposedly, most of the time, alpha is positive or equals to 0. Supposedly. And this method is called the steepest descent method. Sometimes people call this gradient descent. If you are familiar with machine learning, AI, neural network, inside this large problem, they have multiple parameters to be optimized. They call those variables hyperparameters. and they call the procedure parameter tuning. They're tuning, they're trying to find what is the best decision for those parameters. The method they commonly use is gradient descent or steepest descent. Because if they have so many variables, they have thousands of variables. If they try to formulate Hessian matrix, it's thousands times thousands square matrix, and you even want to inverse that huge square matrix. It's too much. So that's why they chose to use a gradient approach like this. So in fact, if you Google for research papers about tuning hyperparameters of neural network, many times they use gradient descent. Of course, they have their approach may not be this simple. They have different strategies to make this convergence faster. This method has a disadvantage. The convergence speed is very slow. I will show you how come it's very slow. Okay? So, for convenience, I'm going to call this alpha k. Because in the next iteration, I will have a different alpha. For every iteration, the step size will be different. So I name the step size or alpha as alpha k for that k iteration. Okay? So, what will be the general solution process? Let's now talk about the solution process. You first will have a initial guess of your xk, and for math we usually start with k equals to 0, but for MATLAB k has to be 1. Now you need to evaluate just the gradient. You no longer need to evaluate Hessian. Then you can apply the steepest descent equation. However, there is something you don't know. You have no idea what is your alpha at this point. So that's just pretend you know. If you know, then you just do your convergence check. If yes, then this is your output. If no, go back. And remember, advance your k by 1. So let me draw the boxes. It's like a flow chart. It's really ugly. Ugly. Diamond. Okay. Too ugly. Okay. Yes. Okay. So, okay. The issue is we have no idea how large alpha is. So we need to create a so-called a sub-problem. We need a sub-problem, a smaller problem to find alpha. So in this procedure, sometimes it's called a line search. Sometimes it's called the alpha minimization. So over here, instead of directly moving forward to the general equation of a steepest descent, we will move to a sub-procedure, sub-problem. When that sub-problem is solved, we will then update what is the best alpha. So this is a sub-problem to figure out how large the step size should be. Instead of directly moving downward, we go to the side, solve a sub-problem there. At the end, we get what is the minimum, what's the best value for alpha, and then come back. Okay? So in optimization, for many times, you may have a flow chart. It's not very straightforward. Sometimes you go to the side to do something else just for certain purpose and then come back. So you can say this main stream is like a main problem, and then on the side is the sub-problem, side problem. Okay? So if you are working on a research that relates to how you define the solution process, you better make a drawing of how the process looks like, so that others can easily understand what you did in the solution process. Don't just describe by text. Sometimes you need to prepare a figure like this to help the reader to understand what happened. Now, I'm going to tell you how we solve the line search subproblem. So for the subproblem, so the idea is when we are inside the subproblem, what do we know? We already know the current x, the solution point at the kth iteration. We know nothing else. We do have gradient, but we don't need gradient at this point. We just need to know this. Okay, so it's we can now go back to see what we're trying to do. We are trying to solve a problem like this, just a simple problem. And oh, I'm sorry, we do need gradient. So sorry, we know gradient already, but because before this process, we know this, right? So let's take a look at the general equation for steepest descent. This is what we want to do for steepest descent. So can we use this equation and then substituting into our function? We actually can. So we can say f of x is close to, we replace x by something we are looking for, the xk plus 1. But we have no idea what is is k plus 1 yet. However, there's an equation highlighted by the pink box. We're just substitute everything into this. We now realize there's something like this. We're just plugging everything. Okay? And what is known? This is known. This is known. Right? They are known. What is unknown? Basically, alpha is unknown. So, if alpha is unknown, this becomes a new formulation. It's a function of a bunch of unknown variables of alpha. So it actually becomes a function of alpha. I will show you one example later on, then you realize, oh yeah, you're right. It becomes a function of alpha. So what we actually need to do becomes minimizing f of alpha. That's why sometimes people call this alpha minimization. Because what is alpha? Alpha is just one scalar, one value, one number. So it's a 1D minimization problem. Okay? So I didn't teach you too many methods about 1D minimization. The only method I taught you was in the homework. It was Newton's method. So over here, I'm just using 1D Newton to solve for alpha. But you don't really need to use Newton. You can use any other methods to find alpha. But it's a 1D problem, just for finding the alpha. So I'm gonna use 1D Newton's method to find alpha, optimal alpha. So it's a subproblem, and inside the subproblem, I have my Newton's iterations. So I will assign n as my as the iteration number for so-called alpha minimization, or we call it line search. Why is it a line search? Because we are now moving toward a linear direction. That direction is the negative gradient direction. We are just trying to find how far away we move by finding the optimal alpha. So we are moving along a line and trying to find how far away we move. So alpha defines how large the step is gonna be. So n is going to be my iteration number, and it's a line search. So let's try to do this. So basically, you are minimizing f of alpha, and you will need an initial guess. So you can have a alpha n equals to 0, and you start with an initial guess, alpha n could be 0. And then you need to evaluate, remember 1D Newton, f prime of alpha n, and also evaluate f double prime of alpha n. Then what? Alpha n plus 1 equals to alpha n minus f prime of alpha n over f double prime of alpha n. That's Newton's method. Its only difference is that the variable now is alpha, it's not x. So convergence check. Absolute value alpha m plus 1 minus alpha m. Is it smaller than 10 to the power of 3? If not, then go back. So advance m by 1. If yes, converge. So the optimal alpha is going to be the last alpha you found. And we will update this value to the main procedure. So at the end, alpha k equals to this guy. So let me show you the box. Draw the box. So it's a general procedure for the line search. Okay. So what's happening is, in reality, in the entirely, what you are supposed to do is gonna be like this. No. No. Okay, it's good. So So overall, this procedure looks like this. So you have, in the main string, you have an initial guess of your x. You evaluate your gradient, but you have no idea what's your step size. So you go to the side, you have an initial guess of your alpha. You need to compute the first order derivative of x and second order derivative of x of f both with respect to alpha. Then use Newton's method. This is a 1D version to update your alpha. Check whether it's converged. If not, do it again until it's converged. The optimal one is the optimal step size. Update to here, then you get what is the best step size for this equation. Then continue for the main process. Okay? Let me show you how we can do it. Solve this by hand, then we solve this by math. Once we're done, we finish for today. So let's try a simpler problem. x1 squared plus 10x2 squared. Not difficult. We know the solution is 0, 0, but we need to pretend we don't know the solution is 0, 0. So my initial guess would be, this time I'm using 2 and 2. Okay? So so k equals to 0 for now. Later on, I will need to know my gradient. So I'm deriving my gradient right here. Okay? And now my x1 equals to my current one minus alpha k equals to 0 times gradient and then plug it in. So 2 times 2 is 4, 20 times 2 is 40. So at this point I have this. Okay, my handwriting of alpha and 2 looks very similar. So I need to be very careful. This is my alpha. Okay. So x1 is a function of alpha, but you have no idea what alpha is, right? So I need to go to the subproblem. For the subproblem, f of x1 actually equals to 2 minus 4 alpha squared plus 10 2 minus 40 alpha squared. Right? I just plug in. So this becomes a function of alpha, like I said. And later on, I need to do f prime and f double prime. So directly try this. F prime would be 2 times 2 minus 4 alpha times negative 4 plus 20 times this would be my f prime. And if you do f double prime, it's gonna be 2 negative 4 and negative 4. 20 negative 40. Okay. This is gonna be my f double prime. Right? So I'm not should I will plug in numbers later on. Okay. So for subproblem, this is already trying to solve the subproblem, right? So initially, I need to make a guess. My initial guess, so I need to be careful, not my iteration number now is n equals to 0. So for easier approach, I'm gonna use f equals to 0. It's okay to guess as 0, right? So alpha n equals to 1 would be my initial guess minus f prime over f double prime. So I'm using 0, so it's gonna be like 2 and negative 4. Right? And over here it's gonna be now truly compute this. Let me try. 2 times 2 times 4 negative minus 20 times 2 is 40. So 1616 over 2 times 4 squared plus 20 times 40 squared, 22,032. So 1616 over 22,030. So it's a 0.05. That's my alpha. Okay? And then convergence check. Alpha 1 minus alpha 0 will be 0.05, not yet converge. So I need to advance my iteration. So m now equals to 1. Advance by 1. Do this whole thing again. Alpha m equals to 2 equals to the previous one, which is this guy, minus a long equation. Right? Actually, yeah, let's try to solve this. 2 times okay. 2 minus 4 times 0.05 times negative 4 plus 20 times 2 minus 14 times 0.05 times negative 40. Okay, so at the end, it's 0.05 minus negative 14.4 over 32,032. So what is 14.05 plus 14.4 over 32,032? It's still 0.05. The increment is so small. If you do the rounding to the level of 0.01, then you stop. You already get the exact same solution, 0.05. So alpha 2 minus alpha 1 now equals to 0, because they are the same. So it's already smaller than 10 to the power of negative 3. So I would say that alpha optimal is 0.05. Okay? So we now want to go back to the original procedure. When we go back, we basically update this equation. This is my general equation, right? So I'm gonna just copy this. So my x1 equals to I'm updating my alphas, right? So it will be so it's gonna be 2 minus this, 2 minus 2, right? Yes. So it's going to be 1.8 and 0. 1.8 and 0. So convergence check. Then it's gonna be 2 norm of 2 minus 1.8 and 0. So you're pretty sure it's not small yet. Continue until it converges. Okay? So that's how it's done. From here you can tell it's actually taking longer procedure by hand, but actually you take fewer derivatives. You don't really need to do second order derivatives. And let's count how many functions we may need to evaluate. You need to do gradient, and like we said earlier, whenever we evaluate gradient, for second order, for cube quadratic problems, you need to evaluate at the same point, and then delta x along x1, delta x along x2. So 3 points. So whenever you compute gradient, this is a 3 function calls, right? And how many we did inside the alpha search? We have to do F prime and F double prime. This is 1D problem. For F prime, we need to evaluate at the original position and then step forward by delta x. So this is 2 function calls. And for F double prime, we need to take one more in the back. So one more right here. But for 1D Newton, solving for the line search, you need 2 iterations. So overall, this is the steepest descent. We take 3 function calls, and then we move to the line search. We do 2 iterations, multiply every time 3 function calls. So over here, totally 6, and here is 3. So every iteration, we overall take 9 function calls. So how much we need for the entire solution process? Basically 9 times the total iteration amount of function calls. We need this. And if we go back to Newton's method, this is steepest descent, but in Newton's method, we basically need to evaluate 1, 2, 3, 4, 5, 6. Totally 6 function calls. And for Newton's method, 2 iterations. So totally 12. So in this simple problem, Newton's method is more powerful. But there is a reason why people still try to use a descent approach. Because when the problem is so large, the issue may not be the derivative. The issue may be the inverse. To compute inverse is taking a lot of time. Okay? So anyway, let's try to visualize this whole thing in MATLAB. Okay. Now, go back to MATLAB. Let's try a 2D problem first. I will use my Newton 2D and then save as a steepest 2D. Steepest 2D. Okay? So same problem, but I no longer need to compute these 3. So I will hide the ones that we don't need to do from the Newton's code. So you kind of see what's the difference. We don't need to do negative delta x. We don't need to do increment on the off-diagonal part. And we don't need the second order derivatives anymore. We don't need Asian anymore. And we are supposed to use Newton's method right here, but now we are going to perform line search here. So once you have the gradient, you need to perform line search. So over here, I'm doing the second while loop inside the bigger while loop. Okay? So now I'm going to have a, I'm gonna do sims alpha, or just A. A is my alpha, just for short, for simplicity. So now I need to plug into the original function. So I'm gonna call this f underline A. I'm going to substitute into the original function, and my variables are x1 and x2, and I'm going to replace them by the expression of x minus alpha times gradient. Okay? So I need that expression of x minus alpha times gradient. So I'm going to have that for now. I'm going to call that XA. So XA is going to be the current x. This is my current x minus my alpha. So I need to have an initial guess. So since my symbol alpha is small case a, so my value alpha is gonna be capitalized A. So capitalized A is my value of alpha. And then I'm going to define this properly. I want this A to be a matrix. No, just vector. Yeah. Before I do that, every time I'm gonna clear A. Because in the second round, my A cannot be the same, the new A. And to be precise, to be programming this properly, you never know how many iterations you need for each line search. Which means if you want to put different, if you want to put different rounds of alphas in same matrix, they may have different length. Because maybe this time my line search perform 3 iterations. Maybe next time it perform 4 iterations. So if you put 2 vectors together in the matrix, but the length are different, then it's troublesome for computer. So let's try not to. There's one way to keep everything all the time. Use so-called a set. So I'm going to define capitalize A, the large bracket K, that's the K cell. So inside the K cell, I can have any length. So over here, I'm gonna say n, but n equals to 1. So at the beginning, m equals to 1. So here I can say n. I need to have an initial guess. Any number, 1. Okay, this is my initial guess. So over here, I will plug in my initial guess times f prime. I haven't have my f prime yet, so I need to do f prime. Oh, I have it. It's right here, the gradient. I have my gradient times my gradient. Yes, it's actually this. Okay, this is what we said. But A right now is just an initial value. Should I plug in the value for now? No, I shouldn't. I should use symbolic for now, so use A. So this X, yes, XA becomes a symbolic function of A. So this is a symbolic function of alpha. And in my code, it's small a, right? So here I'm substituting this into my FA. So at the end, this is my function of alpha. In the code, it's actually FA and the variables are A. Okay? So now I have this function. When later on I need to use finite difference, I will substitute it into FA. So I will need error value, but I cannot use the same variable name. I just gonna say error A and give a large number. While loop. While error A is larger than 10 to the power of -3, I need to do the following. I'm gonna do 1D Newton right here. So 1D Newton, I need to do F prime. So dFA equals to I need an increment. Just subs FA. Now the variable name is called A. And I plug in the current value A. And I'm gonna use the same delta here. So plus del. Right? Minus the whole thing without increment divided by delta. That would be my F prime of alpha. This is F prime of alpha, right? Then I need a DDFA. So I have since I'm gonna use those values multiple times. I need to evaluate those first and then plug in right here. So following what I did earlier, I need to say D of A current and DFA del, and then F of A, and then negative del. Okay. So this guy is this. This guy is this. So I can use those. I can reuse those. Yep. And now I need a decrement on alpha, so I need a minus. Okay? So right here I'm using the del minus 2 times your homework, F alpha current plus the negative one, divided by delta squared. This will be your F double prime of alpha. Now you can advance alpha by 1, so m plus 1 equals to the original one. So here I'm gonna apply 1D Newton method divided by df underline a divided by ddf f double prime. So that's 1D Newton's method. The variable is alpha. Okay? Now you need to update your error value A, absolute value of the new one minus the old one. And you advance your iteration number by 1. So supposedly this will work. And once it finishes, you update your, you just go back to here. You directly have your new equation. But this time, this is your optimal alpha. So your optimal alpha would be this one. Let me see. Since your n will be advanced by 1 at the end, so over here, you don't need to add plus 1 anymore. Your n will be your last one. Okay? So, supposedly, this is the equation. The rest should be the same. Let's try to see if it works. And this is supposed to take a long time. Something is wrong. If it's moving backward, then something is wrong. Initial gas. Initial gas 1, okay, minus A. Increase 1 minus 2 times plus the negative. U1 absolute value. Current 1 minus A times substitute. I need to go to the debug mode to figure out. A, okay. Okay. Hold on. Seems alright. Maybe I try to solve a simpler problem first, the squared one. Just to see whether it works or not. Let's see. Okay. Okay. Yeah. So yeah, it was. I had no idea what happened earlier. Okay, but this was right. Something is weird. Because I was using finite difference. So, if I decrease the delta, it will be better estimation of the gradient. Yes, this is what I'm trying to see. Okay, so over here you can tell the moving direction is perpendicular to the contour because that's the steepest direction. If you move perpendicular to the contour, that's the direction where your function value decreases the fastest. And from the first point to here, the red direction basically is the negative gradient direction. And when we were trying to find alpha, we basically try to figure out, okay, how large alpha should be so that I will stop at some position where the function value is the lowest. So if you pay attention to this line, you will realize over here function value is higher, over here function value is low, and at the bottom function value is high. So for this function, if you move along this red line, it's like a convex problem, right? So along this convex problem, you are just trying to use 1D Newton to figure out, okay, where is the lowest point right there. That's why it's so-called the line search. We are moving along this line. Let me show you if I just keep alpha as a very small value, and let's see what will happen. If I say, even if we, okay, let me make a pause right here. So the optimal alpha is actually .05. 0.05 is the current optimal alpha. But if I replace it by a smaller value, that means our step size will be shorter. So if I replace it by a smaller number, okay, now I just manually replace it, and then we continue. Pause. So you realize I was still trying to move toward the linear direction, but it was 5 times shorter. I manually shortened it. So if I accidentally stop somewhere there, then it's not the best decision. You didn't stop at the lowest point, but you still can continue the solution process. It's okay. If you keep doing this, if you keep on doing this, it will still finish at the right position. But you took one more step because that was not the best step size. The step size was 0.5. Okay? So 1D Newton help us to find the proper distance so we can stop at the minimum point along that direction. We didn't have inverse Hessian to help us to find the best direction. We can only follow the gradient direction. If you have inverse Hessian, you know the best direction is the direction toward the center. If we know, then 1D Newton can directly bring us to this position. But in fact, steepest descent has no information about inverse Hessian. So it can only move toward the steepest descent direction from that current variable. So if I zoom in to show what happened here, you can realize it's always making this 90-degree turns. So it's doing this zigzagging move. Okay? So let's try the 4th order problem again. Earlier, I think I didn't choose the delta small enough. So the estimated gradient led us to somewhere further away. That's no good. So my delta has to be small. Okay, let's try to observe this. Okay, if it's going down, it's okay. But you realize it's not moving to somewhere that is supposed to be the minimum. That's mainly because we still have poor estimation of delta, of the gradient. Okay, it's going to diverge. Okay, it's not doing good enough. So probably I need to decrease the delta even more. Otherwise, it's gonna diverge. Let me try this. Okay, it's power to the fourth is just too much. If I let me try even greater. I'm not sure if this is enough. Or let me try exact derivative. Let's see if this method works. So if I want to use exact derivatives, then I will replace this by gradient equals to DIFF I will just replace these two. So dfx equals to subs diff of f. I just want to see if we can only x, partial derivative of x, right? Only x. Sorry. Only x1. Like this. Yeah. And then y x2. If I replace by these, I should have exact, accurate gradient. Then I may need to do the same over here if I'm not using finite difference, because I noticed the estimation of finite difference may not be accurate enough for fourth order problems. So over here I'm doing substituting, but here I'm doing DIFF with respect to A, yes, and then doing the same thing again. This time this is DF. So I'm replacing the finite difference equation, and I hope this is enough for solving for the fourth order problem. Not a number. Not a number. Not a number. Why? Okay. Let me see. Can we do this? Yes. And can we do this? Yes. So we can get gradient. How about we stop here? Okay, can we do this? Okay. It's a cubic function when we do derivatives. So sometimes because it's a cubic, f prime is cubic, then sometimes it leads to infinity. Okay, so I'm sorry, I better not try this fourth order problem. So how about we just play with sine cosine. I just want to show you some nonlinearity. Okay, and I think we can go back to finite difference. Finite difference. Okay, so finite difference. Should be right. Oh. What? Okay. What happened? Where did I do the pause? Okay. Maybe I shouldn't do something this crazy. Sine problem. Maybe this didn't even converge. That's why it's taking so long. Okay, never mind. Let's try not to give ourselves a problem. Because you know, gradient methods really, they are really afraid of nonlinear problems, concave problems. But simple projective problems is okay. Yeah, let's try to do this in a 3D problem. Let's just try to observe what will happen for the in 3D. Before I jump to 3D, let me just comment in this file so you know what's going on. This was for Newton. This is for 2D Newton. Okay. So later on, if you have this code, you can know what the versions are for, what the codes are for. And this is finite difference, and this is direct derivative, and this is for earlier for 2D Newton. Okay, this is for 2D Newton. Over here, this was for direct derivative. Okay. And this is using finite difference. Okay. So later on, when you have this code, you still can use it. This is for this is 2D Newton. Okay. Now let's get to 3D Newton here. I don't need all of these. I don't need these. Right? I don't need Hessian. Over here I need to do line search. I can actually copy the line search code right here. Just copy the whole thing and then copy to here, but it's not. Let's see. I may need some definition. I need to do symbolic A. Okay. This is okay. Okay, I need 3D right here. And then I think the rest are okay. The rest is the same. Yeah. But I need to update my this line using the steep is decent, so that should do it. Supposedly. And try not to solve a difficult problem like that. Okay, 2D problem. Let's see. Okay, nice problem. And then move forward. Okay, keep moving. Let's see if they are. Okay, it's not moving toward. You don't see the 90-degree turn. That means your gradient approximation is not accurate. So let me get out of the procedure and then reduce my delta by a great amount and then do it again. You're supposed to see that 90-degree turns. Okay. Is it 90-degree turn? Yes. It's taking a while. It's not converging well. I think it's moving around the solution. It's not, okay. I think the delta has to be even smaller. Otherwise, it's taking too much time. Not very well. It's not converging. If you see the error sometimes increase, sometimes drop, that means it's not doing very well. Maybe I have to or let it run. So let's just say draw now. Let me try. Oh, it's not sufficient. Okay. Let's just see. How long does it take to truly converge? Maybe it's the is it really moving? Oh yeah. So along this path is always doing some kind of zigzagging. If we zoom in, it's zigzagging all the time. See? And it's not very effective because if you are not moving toward the right direction and you are just having a angular difference, then all you can do is this. And for quadratic problems, I can show you for quadratic problems. Why is it always following some kind of zigzagging a path? If you look at a quadratic function, initially, let's say your starting point is right here. By observation, you may want to move toward this direction because if you take derivative, that's where you will have the largest function decrement. So you will end up with somewhere along this path, and if you just observe this path, somewhere here would be the minimum, right? And if you take a look at how the contour is supposed to look like, it's gonna be like this. If you do it again for the new position, you will realize you are trying to move along a new direction that is perpendicular to the original path. And then you are trying to move along this new direction, and you may end up with somewhere here. Similarly, if you observe closer and you are moving along this direction, it's perpendicular again. So it's like you are always moving toward the tangent plane of some contour, but the contour is not having the smallest value yet. Okay, every ellipse I'm drawing is like a contour in the space with some function value that is not the minimum. And you are trying to move along the tangent plane, tangent to it. And you will stop at that tangent point because that's where you have the smallest value by line search. From there, you try to move along that contour surface. You definitely want to move deep into the contour. So you are moving perpendicular to that tangent plane. That's why you're making a 90-degree turn. But if that new direction is not pointing to the minimum point, you will be moving along to a new direction that is tangent to a smaller contour surface. So you will keep on doing this until that small contour surface is so small you decide to stop. Right? You will never reach to the real optimum. So you just decide to stop numerically. But in reality, you will keep on doing this. If you insist to stop at the exact point, this method never reaches to the exact point. There's always a smaller contour that your moving direction is tangent to it. You can never point to the right one. But for Newton's method, because for quadratic functions, it has quadratic function information in Haitian. So it knows along which direction you can point to the center. Okay? So that's what happened to steepest descent. Okay, I think that's enough for today. Let's take a look at the homework. See if the problem is good for steepest descent. What was the problem? It was the fourth order, right? Nobody answered. It was the fourth order, so it's not a good problem for steepest descent. So let me give you a new problem. By the way, you know this weekend we have take-home exam. It's already the week. It's already the week. So you better do this homework sooner. If you have questions, you still can ask me. On the day when we have the take-home exam, I'm not supposed to teach you anything. Right? I can teach you something before that, but on that day, I need to be fair. So let's find, let's just say, to some written numbers. Don't tell me your last digit are 9. All those numbers are 9. You're just unlucky. Okay. Use direct derivative. Otherwise, you want to kill me. Not finite difference. Okay? If you use finite difference, you will definitely hate me.
Alpha.
And you use 1D Newton for line stretch. And alpha m equals to 0 can be 0. Okay, so it's life is better. And choose as convergence criteria the limit. Okay, I should not as for convergence criteria. What else do we need? Okay, stop if k equals to, if I say stop when k equals to 4, that means you will be doing it for 3 times. So it's like starting k equals to 0, and then the main procedure. Over here, the convergence check. Over here, k equals to k plus 1. So when you see, oh, that means you will, in the check, when k equals to 4, then stop, right? That means you have done this for 4 times. Yeah. So you need to see if you have your solution process 4 times. I think so. 4 times. Yeah. Okay. Any questions?
I guess let's problem that 3x2. Why not directly 13x2?
Square. Missing the square. Okay. Any questions? Yes, go ahead.
So do we have in the MATLAB code or?
I want you to solve by hand.
Ah, okay.
If you have a code beside you and then you copy the numbers, it's up to you. I have no idea.
Okay.
But I need you to write down the whole thing. You still practice the procedure. If you just use my code and then blah, blah, plug out all the numbers, you still need to write down the, plug in this and that. You still need to do something like this, like what I did right here, right? So my code is just like a calculator. I think giving you guys codes and having take-home exams are treating you guys too nice. Too nice. Well, it's okay. Any questions? Okay, I'm very happy about today because all the videotaping went well and I still have power. Great. let's do the attendance check. So we have, this one already collected, and I already assigned homework 2. And in fact, I'm 1 week ahead. I was supposed to teach multi-dimensional Newton's method this week, but I was 1 week ahead, which is good. So we will do take-home exam on 9th, which is Saturday, is it? Yes, Saturday. So like I said, 9 a.m. in the morning, I will announce the problem. I will announce it on both Moodle and Facebook. If you are not in Facebook or you just don't like Facebook, you need to check Moodle. If you don't see where the problem is, you need to contact me, figure out a way to contact me. And I will announce how you submit. You are supposed to write down everything by hand on paper, and then you will be taking pictures sent to me. If you write down things on iPad, then just take snapshots, either way. Okay, I think I recommend you to do it by hand on papers, because later on, before you submit, I want you to take pictures, and that exact copy, I want you to put it in front of my room. There's a box. It says, take home exam for optimization. I want the real copy. So it's really, I will just check if it's really you. Okay? So if you write it down in iPad, that means you are going to print them out. I still need to see physical copies. Yeah, I guess I would do that. I just don't want people to, copy. You're cheating. I don't want people to cheat. Let me see. Attendance. Oh, by the way, for the range of the exam, basically 1D or 1D or up to 3D Newtons, 2D or up to 3D steepest descent. Okay. For Newtons, if I ask you to do inverse of a matrix, if I ask you to do 4x4, it's too much. So the most I will ask you to do is 3x3. For steepest descent, actually, you can do any dimension. But I guess the most I will ask you to do is a 3D problem. I don't know how many problems I will give away. It depends on my mood. Okay, so let's do a attendance check. So, 嘉伦 ，OK， 俊祥、哲轩、 改君改是云改云改 Harry okay Alice okay William CEO okay Fong Nelly Matthias not here okay so John Wei okay 义军秉承耀宗立慈韦燕甄嬛韦志 Emma Tewaka yes 海琴玉君燕如 Yang Ro okay Joel not here Joel okay am I missing anyone okay are we grouping well right now so Yang Rao and Joel you don't have a group
Number 6. I'm looking to
number
2.
Did I put you somewhere? Not yet. Oh, you're with Adis already? Did I assign that? Oh, you assigned it? So Yang Rao with Adis? Is it correct?
Yeah.
Okay. So how about Joel? He's not here today. Okay, we'll see. So, okay, so far so good. So, Yang Rao, which field are you in?
Intelligent manufacturing technology.
Say again? I mean, which division? Solid mechanics?
Innovation.
Say again?
Innovation technology.
Innovation technology. In mechanical engineering?
No.
Oh, which department?
Intelligent manufacturing technology.
Ah, the special program. Okay. So basically, smart manufacturing.
Yeah.
Okay, got it. Who's your advisor?
I have no private.
You haven't found one?
Yeah.
Okay.
The next is the,
Are you a PhD student?
no, master.
Master. Okay. You better find one soon.
Yeah.
But are you enrolled this semester or the last one?
No. But I'm the new coming student.
So you enroll in spring.
Yeah.
Okay. So you still have a lot of time. Okay. Good. Any questions? Questions? Why so happy?
他在在意他的那个稍微
我写错了吗？哦 break it.
那个
So far so good. So Matthias is not here, right? He's an exchange. Okay, it's fine. He's with the outside. Okay, very good. Okay. Anything else? So far so good? Okay, I'll see you next time, and don't forget about Saturday.